All right, welcome, Chapito. Good morning. Oh, you got some emotes going on. Very cool, very cool. That's I believe, the Poggers emote. Today is Monday, March 23rd. I'm doing a little something different from our calendar. We have to change a few things up. We're going to go ahead and do Flippy number 5 today, do some review, go over a few questions. We have Mastering Physics that is due today, and then I'll show you some simulators again. All right, how's everyone doing today? We have a couple of people. Maddie's up, and Chapito is back. Very cool. All right, so let's go and get started with today's lesson. We're going to talk about parallel plate capacitor. So this is Flippy entry number 5. The title is Capacitance. Capacitance. All right, and we'll start with the top side. The top side is another drawing, and then the bottom side has all the information. So on the top page, or the top side, or this is number 5, so it's the 5th tab. 1, 2, 3, 5. Not including the cover page, of course. That's not a tab. Okay, it's the same drawing, except maybe we're drawing it slightly different in that we have two metal plates. Oh, let's try ink to shape. Ooh. Hey, how come that didn't work? That rectangle is so bad that the AI couldn't recognize the shape. What? It's not that bad. That one was okay. Alright, whatever. There was no place to turn in the worksheet from Friday. What worksheet? Oh, the electric field worksheet? No, that's fine. But the other two you should have turned in, the FET lab and the field drawings. Those are on each day. The worksheet is, we're supposed to, get into groups and teach each other. It's kind of like doing the little presentation stuff we did with the force worksheet. So maybe when we return, we might try to do a couple of these things. But I don't know if you heard, but our schedule has changed, so we'll be back after spring break. Yep. All right. Next up, we're going to draw a big battery. It's almost like a car battery. But I'll draw it in the form of a 9-volt. So basically a box. This one gives you delta V. This is voltage. What do you mean by that, huh? Now I gotta suffer 2 more weeks of online school. Yeah, so our planned closure has been extended 1 more week. So it's this week and next week. After next week, we have spring break, so I won't see you for another 3 weeks. Potentially, school should be opening up after spring break. What is the Flippy called? You just tuned in, huh? There you go. The title is Capacitance. Okay, and you'll need this stuff so that you can finish your Mastering Physics today. There's like at least one, I know, question on capacitors. Well, we don't know that stuff. The governor says a lot of things. He's very well, because like it's not a formal address. He's not addressing the state formally, but he says a lot of things informally. So you have to understand, like, take it based on where he is and who's he's talking to, right? So if it's like his opinion, then yeah, it's his opinion that school should be closed until summer. But there's a difference between giving your opinion and then giving an actual address to the state. All right. Anyway, let's go and connect these metal plates to our battery, like so. Now, typically a 9-volt battery has has a small cylindrical shape. If you've seen 9-volt batteries, you'll know what I mean. It's a little tiny little tube-like shape. And then the other one looks like a rook, a castle from chess. Hey, it's Duyan. It's the first time I actually wake up at 8 a.m. to tune in. Very cool, Duyan. Stop staying up late, then you can wake up early. Aha. There you go. Duyan and all her anime and stuff probably going on at night. Watching all those cartoons. Alright, so in a 9-volt battery, you have this little castle thing on one. Castle thing on one. I go to bed at 4 to 5 a.m. every day, mister. That is not good. So you slept for like 3 hours and woke up? What? On a Sunday? Gintama is what? I don't know. I'm eating Cheerios right now. Very cool. Is it Honey Nut Cheerios or regular? Apparently they're really good for lowering your cholesterol or something. Alright. So let's go and connect the positive end. The positive end is the cylindrical shaped one. The negative end is the one that looks like a castle, a rook from chess. Very cool. Honey Nut Cheerios. We also like Honey Nut Cheerios. Let's go and make some connections. We're going to connect the top plate to our positive side, and then let's go and connect our bottom plate to the negative side. Alright, so this makes the bottom plate. Now the bottom plate is not supposed to be bigger than the top plate, but for some reason let's try ink to shape one last time. Let's see. My ink to shape is just not working. Come on, that's a rectangle, you know it. There we go. It's a little better, I guess. Now the top one looks bigger. Oh my gosh. Alright. Minus, 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 minus. So the bottom plate becomes minus, the top plate becomes plus. Plus, 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 plus. No, stop talking about anime. What did you watch, Giorgio? I was considering watching it yesterday. Okay. Alright. So this is how we created our uniform electric field. Remember, in between these two plates we have a nice uniform electric field. But these are actual devices that we can make called capacitors. This is a separation distance of D, and it's called a parallel plate capacitor. Parallel plate capacitor. Now it's okay, I guess. Technically there are VODs, so you can always rewatch this all over again to get your information. but it's probably better to just do it the first time so you don't have to waste time later, right? A flux capacitor, now that's not actually real, but it allows you to travel time. Whoa! But these are real capacitors. Real capacitors hold charge. They hold charge. And typically what you do is you roll them up, and then it turns into like a cylindrical shape thing. And, ooh, need to shape is on. That's not very good. And if you see it, the bigger ones are, cylindrical shape. They have little legs, stubby legs. Now we were able, for like motherboards and other circuit boards, these things are so miniaturized they might look like little tiny rectangles, and you might not be able to recognize them. However, most circuit boards use like similar codes, so that if someone needs to make a repair on the board itself, they'll know what they're looking at. So they'll use things like capital C, and that'll tell you that, oh, that's a capacitor. So it might look like a tiny little rectangle if you look at your computer motherboard or something, and you'll see that there's little C's, little F's, there's some R's, and we'll learn what all those things mean next unit. Okay, so anyway, this is a capacitor. Capacitor. All right, and we want to write a few equations. So let's see. Delta V, the voltage that you use, is equal to the electric field that is inside the plates, inside the middle of the plates, times the separation distance d. Typically, there's some sort of insulating material in between called a dielectric, but air is, I guess, also, usable. So you could just have air in the middle. It doesn't really matter. But putting different materials will change the amount of charge that each capacitor can hold. So we can control how much of a capacity each capacitor can have. Okay. And the other equation is Q, which is your variable for charge, is equal to C times V, and that delta V. Alright, so now we have a bunch of variables, so we have to make sure we understand what each thing is, and that'll be at the bottom side of your Flippy, so stay tuned. We'll also go ahead and throw this at you. This is called a circuit symbol, and we'll learn more circuit symbols next unit. The circuit symbol, for a capacitor is, it's basically two flat lines that the symbol itself represents the two metal plates that we have. So two lines that are similar length, like this. You can have it in this orientation, or you can do it in the vertical orientation, like this. Alright, so that's the top side. Here's the bottom side. Bot side. The bot side is the information, so let's start with our first bullet point. A capacitor is a device. A capacitor device that shows the electric potential that stores charge. It's almost like a battery. Batteries store charge and then you get it back after you discharge it. But capacitors have a different process, physical and chemical process. Batteries have a chemical process, whereas capacitors are completely physical. They are much faster, so you can discharge and recharge really quickly. So if you need a bolt of energy, a flash of light, you can instantly get it by discharging a capacitor. My dog is back for physics. Excellent. Did we rename your dog? Oh no, his name is Leo. So Leo's good enough. We'll keep it at Leo. He's the Leo the physics dog. He has his own equation. A capacitor is a device that stores charge. Okay. Parallel plate capacitor is two plate. Okay. A parallel plate capacitor is two parallel plates separated by a small distance d. See figure 1. Oh, did we label this thing? Oh, whoops. Let's go and label this. Figure 1. There we go. Let him become a mascot for physics. Ah. I will consider it. Alright, a capacitor is energized with charge Q. When a voltage delta V is applied. At the terminals. Hey, we just got a follow. Cool. Adam Zane Physics AC account. Ay. Cool name there, buddy. At the end of the stream, is it possible you could do a mastering physics problem? Sure. Alright. Okay, make sure you subscribe on YouTube, because we need those YouTube subscriptions to hit 100. Alright. The terminals are the top and bottom. Of the parallel plates. So in our picture, you can see these little black probe things. They're connector pins. And these are the terminals, essentially. They allow you to connect to the battery. Yep. Alright. At the terminal, top and bottom. Capacitance is defined as... Oh, now everyone is following. Cool. Hey, there's Angela. Capacitance is defined as capacitance. Okay, this is... basically the ability of a capacitor to hold the charge. A bigger value means it can hold more charge per volts, or per the amount of voltage you use. Capacitance is defined as C equal to Q divided by delta V. All right, so let's take a look at all of our variables. C is called the capacitance. Okay, this is the ability to hold charge. Okay. And it is measured in units of capital F. Uh-oh, you got to be careful. This is not force, these are units. It's called a farad, and I'll write it in the next bullet point. Okay, Q is the same Q you've been using. This is the variable for charge. For parallel plate capacitors, Q is just the charge, the magnitude of the charge on one of the plates. Alright, so this is the thing that you need, Duyen, for question number 9 on Mastering Physics. Charge on one plate. And chat, what are the units for charge? What do we use for charge? Ooh, can someone tell us? What do we use for charge? What are my units? Yes, Speedy Cat, very good. It's capital C coulombs. Delta V, yeah. Who is Speedy Cat, by the way? Since you got it first, we'll give you a wireless high five. Wireless high five for Speedy Cat. Delta V is equal to, well, delta V is the voltage itself. I thought you purposefully seen my email. Yes. Applied voltage. Okay, and that is the delta V, measured in V. V is the only thing that is measured in V's, volts. Alright, so those are our variables, and this new unit, capital F, is called a farad, or farads. The unit for a capacitor, so for capacitance is the farad. Yeah, make sure you guys wake up early and tomorrow so that we can do like a quiz bowl tomorrow, and that'll be cool. But if no one shows up, then it's just like, you know, me and Chapito here, who wakes up early in the morning every day. So everyone, make sure you're up and running by 8 o'clock tomorrow. Farad, and that's capital F. Okay. Well, not a traditional no. The answer is no. But we'll do something. Like we'll do like a Canvas multiple choice or something. No, spring break is only for fun and relaxation, of course. If you like working during spring break, consider. No. I will introduce at least the projects that we'll work on, so that you can get someone started over spring break, but not like no like homework packets or anything like that. So I'll just I'll introduce the projects at least, so you can start gathering material, start brainstorming what kind of design you want to do. And remember, these projects are worth test grades, so this will definitely help us. Do we have a test soon? Oh, our calendar says Wednesday, so I will make sure you're up bright and early, and then I'll tell you how we're doing it. A big Kahoot game. Well, the Kahoot game is tomorrow, so make sure you play tomorrow so that you're ready. we'll do like a small online type of quiz thing, but not a full test. Um, we'll just kind of postpone all of our exams, like the primary big exams, over until we actually come back to school, and then we'll just combine everything together. Yeah, so that's the plan. But until then, the most you'll have is like a small, multiple choice type activity. We'll call it an activity. I don't want to call it a quiz. No, do not do it. I have to make sure you're learning something, right? So, some of you are just watching anime all day. How am I supposed to know you're doing some sort of physics? So this is the only way I'll find out. So I have to do it, Chris. It's not for me, it's for you guys. Alright, so the unit is capital F farads. And then let's finish this off. You can trust us, Mr. Oh, sure. One of my biggest character flaws is that I have trust issues. Then do a Kahoot or quiz game that counts for our test. Wow. That is a very low stakes offer. I'm not sure I want to take that. The capacitance of a capacitor is constant. The capacitance, so the ability to hold the charge of a capacitor, something that holds charge, is constant. So this is a material property. Once you make the capacitor, once you build it, based on what kind of materials you use, you've kind of established the capacitance, how many farads it is. Teachers aren't allowed to make us log in at a certain time, Christian. That is true, but we can also put due dates on whatever the assignment is uploaded, so you have at least, whatever day that you're working on. So there's always a loophole, Adam Zane. I want to do a video chatted conference. Oh, really? Yeah, I think some teachers have done that using the Teams or Zoom or whatever it is. Whatever everyone is comfortable with. I'm not sure I am comfortable with video right now. I'll have to figure out a new setup so that it's like an office room or something. Who are you? What period are you in, Adam? Adam's in 6th period. Alright, and finally, the electric potential energy of a capacitor. Remember, it holds charge. So there's another way to find the electric potential energy. I typically use PEC. This is the potential energy of a capacitor. And it's equal to 1/2. It's almost like all the other ones. Nah, I'm not. I'm just not. As I think some students are just not comfortable with using their video. I know some students have taped their video their camera shut. Well, 1/2 C delta V squared. Okay, this is not velocity, this is capital V. This is the voltage on your battery. Okay, so 1/2 times the capacitance, which is measured in farads, times voltage squared is your energy. No, they don't have their camera or webcam on, or microphone, exactly. But the other thing I want to say is, as students, you are required to log into Canvas every day. And so if we have a participatory-like activity for Wednesday planned on Canvas, then you have to make sure you log into Canvas on Wednesday to participate in that activity. A participatory multiple choice-like activity. Alright, so that's the bottom side. That's about it. So let's go and review. On the top side, we have our drawing of, here's our parallel plate capacitor. So I'll open it up exactly at midnight on Tuesday. And the drawing on the right side is what a real one kind of looks like. Yes, Christian, yes. So the one on the right is like a cylinder. This is like a real capacitor. And here's a parallel plate capacitor. The symbol are two parallel lines here. Capacitor is a device that stores charge. A parallel plate capacitor is two parallel plates separated by a small distance d, and that separation distance does matter. Capacitor is energized with charge Q. Remember, Q is the variable for charge when a voltage delta V is applied at the terminals. Capacitance is defined as C equal to Q over delta V. So we're basically using this equation, Q equals CV, and isolating C. Capacitance C, which is in farads, and then capital Q, of course, is charge measured in coulombs. Delta V is our applied voltage V. And the unit for capacitance is the farad, capital F, in our equation. All right, so that's it for Flippy number 5. Title. Here it is. Capacitance. Okay, so we had one question already asked, question number 9 for Mastering Physics. So I'll do some Mastering Physics help, and then we'll be done for the day. So here's Mastering Physics help now. Mastering... Oops, stomach's growling. I gotta eat breakfast. Let's end the stream. Mastering Physics. Number 9 says... a capacitor with a capacitance of 750 microfarads has a charge of 56 and negative 56 on the other plate. When you're using the capacitor equation, you're only looking at magnitude of one plate. Okay. Remember, when one plate is positive, the other one is automatically negative. So if this is like plus Q charge, this one is automatically negative Q charge. Of course, together, it would be zero charge. It's neutral. But you know, when you're using the capacitor equation, you want to use one plate at a time, otherwise it doesn't make sense. 0 equals CV. So the Q represents the total amount of charge in magnitude of one of the plates. Yeah, charge, force, field, potential, and now capacitance. All right. And so it says, what is the potential difference between the plates? So this is number 9. Ooh. Number 9. What is the potential? We'd love your feedback. Not now. Go away, Microsoft. So we're looking for potential difference. So another term for voltage is called potential difference. Potential difference. Okay. And that is delta V. Okay, so we're looking for delta V. If I use my Q equals CV equation, Q equals CV, and then isolate my variable, you get Q over C. So delta, so let's start with the general equation. Q is equal to C times V, and therefore what we're looking for, delta V, is equal to Q over capital C. Q is the charge of one plate. Charge of one plate in coulombs. This thing is not coulombs. It is the capacitance. That's the variable. Capital C as a variable is capacitance. Capital C as a unit is coulombs. Capacitance in farads F. So if you're given things in micros, make sure you convert them first. Micros or picos or nanos. Sometimes you can get away with it when the micros cancel, but I don't want you to bank on a sometime. Just convert it, put everything into standard, because I might use nano instead of micro on one of them, and you might forget to convert. So just train yourself to convert everything into SI units. So if you have microcoulombs, make sure you convert that into 10 to the minus 6. So remember, micro is 10 to the minus 6. Alright, so this is just a plug and chug, Q divided by C, and that should be it. Adam Zane, you had a question? Go ahead and ask now. This is the Mastering Physics session. Number 14, alright, number 14. Let's take a look. Number 14, it says, 3 charges are located at the corners of a rectangle as shown. Wow. K is blah blah blah. Okay. What is the electric potential at the empty corner of the rectangle? Ah, yes. So this is similar to the practice problem we did in our electric potential video. Did you watch that video, Adam Zane? The electric potential one? Well, basically, when you're doing electric potential, electric potential is V by itself, not delta V. The potential difference is delta V. V by itself is equal to, for point-like charges at least, K times Q over R. KQ over R. Yeah, make sure, if you didn't, you gotta watch all of them. Subscribe, hit a thumbs up, give us all those good stuff, and learn all of the physics that you need. Electric potential, KQ over R. Remember, this is a scalar, so you don't have to worry about vector components. You can just add them up. However, if you have a positive charge, you have positive voltage. If you have negative charges, you have negative voltage. Or potential. I shouldn't say voltage. You have positive charge, positive potential. Negative charge, negative potential. So if you have 2 negatives, so these red ones are negatives. We have 1 positive, and we're trying to find this thing here. Let's go and label them. We'll label this number 1, number 2, number 3. So V total must be equal to V1 plus V2 plus V3. Okay, so this would be K times charge 1. Make sure it's in standard SI, so convert the micro into 10 to the minus 6. KQ1 divided by R1, and R1 is equal to 0.16. Okay, the distance from charge 1 is 0.16 meters. Plus, well, let me just plug in. Actually, let me write it first. Shoot. R1, this one would be K, Q2, R2, K, Q3, R3, and the distances are different. So this is 9E9 times Q1, whatever Q1 is for you, divided by the distance, 0.16. Actually, I think the Q's are the same on this one. Adam, can you verify? Is yours 2.7? Is the 2.7 micro for number 14? Charge 1 on the top right. Yes. Oh, okay. So this would be 2.7 e negative 6. All right. Plus 9e9. Now the second and third charges are negative, and for voltages or potentials, make sure you plug in negatives. If you look at make sure you watch all the videos, because we made a really nice equation chart that will help you remember all the equations and remember how to go from one equation to the other. So make sure you watch all the videos. Negative 6.1 e negative 6 over the distance from number 2. How far is number 2? Whoa. Well, to find the distance for number 2, you have to do Pythagorean theorem. So make this into a right triangle. So this distance is equal to the square root of 0.16 squared plus the other side. What's the other side? 0.25. Okay, so that's R2. R2, you have to use the Pythagorean theorem to figure out what that distance is. Is this a 3, 4, 5 triangle? Oh, no, it's not. The base is 25. Darn it. We'll just call it R2. Whatever that is. And finally, 9e9 times negative 3.3 e negative 6 divided by R3, and the distance for R3 is 0.25. Okay. Remember, the denominator is just R, there's no square, so it's just KQ over R, and then you can just add them up and that should be it. Alright, I guess that is all. We'll play Quiz Bowl tomorrow. Make sure you're up by 8 o'clock. Can you do number 5 as well? Sure. Dewey and Lee, number 5. 2-point charges of equal magnitude are 8 centimeters apart. At the midpoint of the line connecting them, their combined electric field has a magnitude of 45. Okay. So, conceptual questions. Wait, that's just a multiple choice. So either I give you the answer or I don't, right? Let's see. For conceptual questions, you can use the simulator. So if you go to the FET website, Simulation Physics, and use the electric field simulator to answer all of these. Okay? If you have two opposite charges, you'll see that the electric field is not 0 in the middle. Okay? But if you have two same charges, like plus and plus, oops. Ooh. I can use our sensor. Okay, if I put the sensor directly at the middle, notice how the sensor's arrow disappears. That tells you that the vectors cancel out, giving you 0 electric field in the middle. Okay, so of course they're same charge. Part B. Oh, okay, Part B. Part B says, what is the electric potential at the empty corner? Oh wait, that's number 9. I'm reading the wrong one. Here we go. Part B. Find the magnitude of the charges. Okay. 2-point charges of equal magnitude. So you can call it Q and Q. So you can say K times the same charges. If Q and Q are the same, Q times Q gives you Q squared. KQ over R, KQ squared over R squared Wait a minute. That's not right. We're doing electric field. KQ over R squared is the electric field, right? Alright. And it says the 2-point charges are 8 centimeters apart. Now, your number might be different. Okay. But in any case, set that equal to E, and then solve for Q. So E times R squared over K equals Q. All right. So E is given. Go ahead and plug it in. K, is a constant, and then solve for Q. I guess that's it. Yeah. All right. That'll be it for today. Thank you for tuning in. I'll see you next time.